Welcome, everyone. Today, we aren't just looking at a syllabus, we're looking at a strategy for dominance. For the International Cambridge Chemistry A2 levels, success is decided by how well you handle complexity. To start, I am giving you the top 5 topics to master if you want to secure that A in 2026. We've analyzed the shifting weightings of Paper 4 and Paper 5 to identify where your study hours will give you the highest return on investment. Before we dive in, look at the field. Paper 4 is a 2-hour marathon worth 38.5% of your grade, demanding total synthesis of theory. Then there's Paper 5, only 11.5%, but it's pure strategy. You don't perform the lab here, you architect it. You'll be assessed on accuracy, reliability, and scientific reasoning, rather than just physical execution. Applying the Pareto principle to the 9701 syllabus, these are your 5 core pillars: organic synthesis and mechanisms, reaction kinetics and thermodynamics, transition elements and electrochemistry, analytical spectroscopy, experimental planning and evaluation. Master these, and you've mastered the exam. One is about route design over rote memorization. Identifying a functional group is just the baseline. The real marks come from devising and analyzing multi-step synthetic routes for complex molecules. You need total mastery over free radical and nucleophilic substitutions to create complex nitrogenous compounds like amides and amino acids. Examiners are looking for your justification of specific conditions and reagents, as well as your ability to predict properties and byproducts. Before we move on, let's talk about your final prep. You can know the theory, but the exam is a different beast. At Blackwood Prep, we've engineered our 2026 A-level predicted papers to bridge that gap. These aren't just practice questions. They are data-driven simulations of the actual papers you're going to sit. We've included the exact unfamiliar contexts and tricky synoptic links that catch students out every year. If you want to walk into that exam hall with 100% confidence, grab the predicted papers at the link in the description. Invest in your grade. Now, back to the lesson. Pillar 2 covers the mathematics of chemical change. This is where theory meets high-level calculation. You must be lethal at deducing reaction orders from raw data and proving rate-determining steps via proposed mechanisms. Beyond kinetics, you'll be calculating reaction feasibility using Gibbs free energy and navigating the complexities of pH for buffer solutions and solubility products. In these multi-step calculations, rigorous unit tracking and adherence to significant figures are absolutely mandatory. Pillar 3 is what we call the common last topic. It's often rushed, yet it is disproportionately tested. It generates the hardest 15-mark structured questions you will face. You need to be able to explain the origin of color through d orbital splitting and energy gaps, predict feasibility using stability constants, K-stab, and use the Nernst equation to calculate non-standard cell potentials. Precision in writing complex formulas and half equations is non-negotiable here. Pillar 4 is molecular forensics. This is pure structural deduction. You aren't just identifying an alcohol. You are using proton and carbon-13 NMR to deduce adjacent protons through spin-spin splitting patterns while justifying the use of deuterated solvents. You'll use mass spectrometry formulas to calculate the precise number of carbon atoms and move beyond simple identification in infrared spectroscopy to predict absorptions using specific wave number data. Guesswork is heavily penalized. Every shift must be systematically justified. Finally, Pillar 5, experimental planning. Remember, you aren't doing the lab. You are architecting it. An A plan requires 4 things: a clear hypothesis linking your variables, explicit definition of those variables with specific units and ranges, apparatus precision, choosing volumetric pipettes over measuring cylinders, and a realistic risk assessment that identifies actual hazards, like using fume hoods for hazardous gases. The evaluation section is the examiner's ultimate filter. You must master graphing protocols, plotting y against x and identifying anomalous points derived from line of best fit deviations. You must understand that repeats improve reliability, while upgrading apparatus precision improves accuracy. Most importantly, avoid vague answers like, "Be more careful." To score the mark, your improvements must explicitly state how a specific modification fixes an identified error. Notice how your knowledge must pivot between papers. In Paper 4, you might calculate a rate constant K using the Arrhenius equation. In Paper 5, you're designing the actual experiment to track that gas volume over time, specifying syringe capacities and measurement intervals. Whether it's thermodynamics or redox, you must be fluent in both the theoretical demand and the practical execution. The best candidates see the syllabus as an interconnected synapse map. Top-tier marks are awarded to those who can navigate the intersections, synthesizing a transition metal complex, modeling its rate of exchange mathematically, identifying it via NMR, and then spotting anomalies in the resulting data. Don't study in silos. Connect the dots. Vague language kills grades. Saying results are wrong because of heat loss is weak. A strong candidate specifies, quote, systematic error due to convection heat loss, and suggests utilizing a polystyrene cup with a specialized lid to improve accuracy. Similarly, don't just say peak shows in alcohol. Specify the broad IR absorption at 3,200 to 3,600 centimeters carat -1, indicating hydrogen bonding from an OH group. And always check your units and significant figures against your least precise instrument. We leave you with 3 final directives for 2026. First, integrate. Never study pillars in isolation. Second, simulate. Treat Paper 5 like architectural drafting and physically write out full plans with apparatus diagrams. Finally, execute. Focus on structural logic over surface-level recall. Build the framework, understand the connections, and execute with precision. You have the blueprint. Now go get that A.